ठीक है. Okay. Hi, uh, welcome you all to this live interactive session for week 6 of the course Structural Geology offered by NPTEL. My name is Rajiv Mukherjee and I am currently hosting these live sessions. And today's topic of discussion is deformation mechanisms. So this is the course outline as we are already doing it. So we have already covered 5 weeks worth of content, and for the week 6 we will be discussing about deformation mechanisms of materials and rocks. And this is the live interactive session. Today's date is 31st of August 2024, and the time for this live session has been fixed to 4 p.m. to 6 p.m. every Saturday, and this is the link to join the discussion session. So without any further ado, let us proceed for what we have learned in this week 6. So if we summarize what was the content for week 6 for the course Structural Geology, it was mainly talk about deformation mechanisms of crystals and deformation mechanisms of materials as whole. So we learned that from a perspective. So there is a new philosophical perspective has been pointed out towards you, and that being that every deformation that we see in rock, they are the consequences of cumulative deformation of single crystal deformations. Those are known as intracrystalline plastic deformations. So material behavior on a large scale, or we can say on a bulk scale, it can either be brittle or ductile. That means there can be a loss of cohesion, but there cannot be loss of cohesion as well. However, the deformation or the rheology of the material that we see, it often becomes elastic, viscoelastic, viscoelastoplastic, or linearly viscous. So these kind of things, they are safe to say that those things are a pretty large scale manifestation of individual discrete events that take place in form of crystal plastic deformation. So whenever we talk about deformation mechanisms that are involved within crystals, you should keep in mind that these deformations can either be elastic or plastic. Crystal as a single grain, they tend not to show any viscous components in their deformation. So it either will be plastic or either will be elastic. But as a manifestation of these interactions between different grains in a polycrystalline system, we often interpret the bulk deformation to be viscous or viscoelastic or viscoplastic. So on that direction, we can say that the summary of week 6 content was mostly related to the concept of crystal defects, starting with point defects, line defects, and surface defects. Then we talked about the concepts of dislocation, which are again divided into edge dislocation and screw dislocation, dislocation loops, stacking faults, grain boundaries. Those are the surface defects. Then we talked about deformation twins, granular and cataclysmic flow in brittle regime. So this granular and cataclysmic flow in brittle regime, they generally talk about bulk scale of deformation. And then we talked about strain localization in brittle ductile regime, dilatant and non-dilatant deformation. And then for crystal plastic deformation mechanisms, we talked about dislocation glide and dislocation creep, flow laws in dislocation creep regime, diffusion assisted dissolution precipitation creep, diffusion creep, Navarro herring creep, and cobble creep mechanisms. And mostly we learned about the basics of how the flow law is being formulated and keeping in mind the energy balance of these four flow laws. So the flow law is a dynamic or a constitutive equation that tells us about the thermodynamic condition of the system. So any kind of flow law that essentially leads us to the estimation of free energy that has been available in a system that allows the material to respond in terms of external forces and then they present this kind of viscoelastic or viscoelastoplastic deformations. And then finally, we talked about the application of deformation mechanisms in geodynamics and planetary sciences, especially for tracking the age of the mantle and how from thin section and observing different grains of crystals such as garnet and other zoned crystals, we can estimate about the diffusion of materials or trace elements from mantle to the crust and so on. So there is a huge implication of these deformation mechanisms in understanding the geodynamics and planetary evolution in our solar system. So today's topic of discussion will mostly be related to solving conceptual problems related to deformation mechanisms of rocks and materials, and then we will summarize and conclude today's session, and then we will also discuss briefly about the plan for upcoming live session. So we will start right ahead with the MCQ questions. Okay, so today's first question of this live session is that which type of defect will be absent from an ionic crystal? And the given options are Schottky defect, screw dislocation, interstitial atomic impurity, and grain boundary. So these are the four options, and you may answer which can be the correct from these four. Keep in mind, we are talking about ionic crystals, not covalent crystals. Any idea what can be the answer?
So it will be grain boundary.
No, because any lattice will eventually have grain boundaries, because lattice grain boundaries are essentially free surfaces. So grain boundaries are basically, if you are talking about a polycrystalline system, then grain boundaries are basically can be two things. So if I write about what are grain boundaries in a polycrystalline system, grain boundaries can be two things. Number one is misorientation of crystal axis that leads to separation of two different crystals. This can be one thing, or another one could be the interface between two crystals of different chemical composition. So the misorientation and the presence of another phase both can lead towards the development of grain boundary, and that is quite normal in both non-ionic, covalent, and ionic crystals. Okay, so these features, that mean grain boundaries, which are surface defects, these surface defects are essentially of mechanical origin, right? So any kind of defect that originates from a mechanical heterogeneity in a system, that can occur in both ionic and covalent crystals. Right? But there are certain things that are chemically controlled, and that means for ionic crystal, the presence of the electric field and the would actually hamper the presence of such kind of defect. So that being is completely another issue, which is essentially related to the point defects, right? So point defects are something that are related to the chemical impurity and entirely with the composition of the crystal itself. So point defects does not have a mechanical origin. See, dislocation or grain boundaries, these kind of things, they are associated with mechanical origin. But compositional heterogeneity would only affect the point defects. Otherwise, dislocation and this one and grain boundary, they are mechanically originated defects. Mechanically produced defects. Hence, they are present in both ionic and non-ionic crystals. So what could be the answer? So I told you that mechanical heterogeneity will not lead to any kind of differentiation between defects in ionic and non-ionic crystals. So the only thing that can take place is the point defects, right? So if I classify point defects, then again point defects can be classified based on the bulk composition, whether it is non-ionic or it is ionic crystal. Sorry.
Option A is right then.
Option A, no. Schottky defect is a feature of ionic crystal.
ionic crystals का feature होता है ना sir?
But the question says is that it will be absent from an ionic crystal. So for ionic crystal, the general point defects that we see are Frankel defects, Schottky defect, and another is electron hole pair. That leads to the formation of semiconductors. So these are those electrons and hole and their energy exchange and their distribution within the material can lead to the formation of semiconductive materials such as like germanium or silicon. So those are ionic crystals and they essentially have this kind of electron hole pair structures as point defects. Now coming to the non-ionic crystals. So for non-ionic crystal, point defects can originate in two types. Either there will be an absence of an atom, so that is vacancy, or an unwanted presence of another atom, that is impurity. So vacancy means there will be an absence of an atom or a molecule. And impurity is there will be an unwanted presence of an atom or a molecule. That means they are out of place. So impurity will be in a form that either the diameter or the ionic radius of that particular atom is different from that is present in the crystal itself, or the molecular size of the molecule or the impurity that has been implanted into this crystal, it will be different. It will either be smaller or larger than the present structure. So it will be distorting the stress field around that point where the impurity is being placed into the crystal. And the same goes for the vacancy as well. So this creates an energy field that is either being very low from the equilibrium position or very high, and that would lead to the instability within the crystal, and eventually the point defect will propagate in particular direction to mitigate this energy disbalance and eventually come to the equilibrium condition. So impurity are again classified into two categories. One is interstitial impurity, and the other one is substitutional. So then it is very much clear that interstitial atomic impurity, it won't be present in a ionic crystal, and that means option C is correct, which is that interstitial atomic purity will not be generally present within an ionic crystal. Okay, moving on to the next question. So we talked about twinning in the crystal defects, and twinning is kind of a surface defect. So there is a table given for different kinds of twins: A, Braveno twin; B, polysynthetic twin; C, cyclical twin; and D is Dauphin twin. And the given minerals that commonly present these kind of twinnings are plagioclase for P, Q is orthoclase, R is quartz, and S is chrysoberyl. So you have to match the left side of the table to the right side. And the options are given as option A is equal to Q, B is equal to P, C is equal to S, and D is equal to R, and eventually the other options are also present. So what could be the right answer? Any idea?
माइक्रोक्लीन्स में सर ब्रवीनो ट्विन्स होता है सर, माइक्रोक्लीन या ऑर्थोक्लेज में होगा सर, A Q.
Yes, exactly. A is Q. So that means option A is correct, right?
Yes sir.
Okay, very good. So option A is correct. Now the thing is, what kind of twins these are? So Braveno twin, polysynthetic twin, cyclical twin, these kind of twins, these are contact twins. So if I classify them, Braveno, polysynthetic, and cyclical, these are contact twins. And Dauphin twin, it is a penetrative twin. Okay, so So talk about Braveno twin. So this twin occurs for orthoclase following the zero to 1 set of planes. And this Braveno twins is a planar surface that separates two compositionally different phases. Right. Now talking about contact twins are again classified into two categories. One is polysynthetic twin. So for polysynthetic twin, the compositional surfaces across the twin boundary are parallel to each other. And one of such example is the is L white. Example is L white showing 010 twin planes. So that means for L-bite, the twin plane will be perpendicular to the B axis of the crystal. And this twin is known as the L-bite twin law. And of course, polysynthetic twin, since it is observed in L-bite, so it is a common feature for plagioclase, right? Because L-bite is a plagioclase group of mineral. So Braveno twin goes for orthoclase and polysynthetic twin goes for plagioclase, right? And the other division is number 2. This is the cyclical twin. So cyclical twin is that the compositional surfaces are, across the twin plane intersect each other. Right. And so that means the twin boundaries, they occur as crisscross pattern. And one such example is chrysoberyl. The 031 set of planes of chrysoberyl is such example of cyclical twin. So C goes to S, and eventually the dauphin twin go for R. Now, what is dauphin twin? Dauphin twin this is a deformation twin and hence it is penetrative. Right, because these Braveno twin, polysynthetic twin, all these kind of contact twins, they are essentially originating from compositional heterogeneity. So these kind of twins can even occur for undeformed crystals as well. But dauphin twin is a signature of the variation in pressure and temperature experienced by quartz, and therefore dauphin twin is a penetrative twin because the contact twins are not penetrative, right? But dauphin twin is penetrative, and the this kind of twin is also called transformation twin. That means they originate from the transformation from one thermodynamic condition to other. So if you increase the temperature, or even if you increase the temperature and pressure and apply some external stress, the quartz grain will eventually deform and produce the dauphin twins. And dauphin twin generally shows the twin law is 0001 planes, I mean direction for hexagonal system. So keep in mind, dauphin twin is a deformation twin, whereas Braveno, polysynthetic and cyclical twins, they are the signatures of contact twins, which are chemically controlled twins. So chemically controlled twin can even occur independent of the deformation of the material. But dauphin twin will explicitly occur because of the deformation of the material.
Sir, there
Yes.
is a question. Sir,
Yes.
if albite is in stress condition, it will again show polysynthetic twin. If it is in stress, under section, it will show.
Yes, it will obviously show polysynthetic twin, because for albite, this compositional heterogeneity will only occur because when temperature, because of difference in temperature. So you know about the exolution lamellis that we see, exolutions lamellis and these kind of textures. They occur because of the exolution between the microcline and albite, right, in certain temperature conditions. So that is mostly controlled by the temperature. So if you fluctuate the temperature, it will eventually produce these twins, right? These exolution structures that are essentially followed as twins. In case of plagioclase, you also see that. So the key role of the thermodynamic parameter is temperature. Now, if you increase pressure, it will eventually lead to the formation, provided that with that at that particular pressure, the exolution status or the exolution temperature will also change. So eventually you have to rise the temperature as well. So if you keep the temperature constant and increase the pressure, that means you're applying certain lithostatic pressure or applying some stress, you will eventually end up not producing the polysynthetic, this polysynthetic twin in plagioclase, because it will exceed the, the exolution temperature will change. But for a constant pressure, if you keep on increasing the temperature, it will obviously, if you fluctuate the temperature, it will either increase or decrease with the exolution temperature, and eventually it will again produce the polysynthetic twin. So the main the twinning is the function of temperature explicitly, but it also depends on pressure. So if you simultaneously increase the pressure and temperature in linear fashion, then you will end up producing the polysynthetic twin in every set of stress condition. But if you keep constant one of the parameters and change the other, you may not get the polysynthetic twin. But that won't be a signature of the stress only, because there is a component of temperature as well. Okay.
And second small thing is that what will be the difference between polysynthetic and lamellar twin?
They're same.
They're same.
Yes, they're same because it mostly
Parallel.
they're defined as they are contact twins, and contact twins which are which generates parallel surface. They are same.
Okay.
Hmm. So moving on to the next question, it says, during a localized cataclysmic flow, which of the following external parameters could change the deformation from compactional shear to dilational shear? Option A is change in tensile stress regime. Option B, plastic deformation of asperities. Option C, increase in pore fluid pressure due to external fluid injection. And option D is grain size reduction. So which of the thing? So again, I must say that for compactional shear, we see a localized zone, and these are cataclysmic grains, which are called cataclysmites eventually. And there is a constant shearing as well as compression. And so what will happen is that for compactional shear, this width of the shear zone will decrease. But for dilational shear, the width of the shear zone will increase. Now the point is that this compactional shear and dilational shear, we are talking about brittle deformation, right? We are not talking about the ductile shear zones. These are brittle shear zones. They are completely different from ductile shear zone. In case of ductile shear zone, there can be an existence of compaction or compression, and still the shear zone can widen based on the hardening component of the shear zone and other crystal plastic deformation signatures. But for brittle shear zones, which are mostly, which are mostly governed by the cataclysmic deformation mechanisms, in that case, we deal with granular materials and crushed grains that which has no cohesion in between them. So this is not a kind of ductile deformation. It is essentially a brittle deformation, right? But in this case, whenever we are trying to widen the shear zone, I mean, we're talking shear zones in the sense that the maximum shear is being localized in a particular area. And if you just want to expand that region, that means we want to expand the volume of the entire area, which would require dilation. So it, of course, is a change in the stress regime. But is it the change in tensile stress regime or something else? That is the question.
But if we increase the pore fluid pressure due to external fluid injection in some hydrothermal fluid, then this width will be increased, no?
Yes, exactly. So the increase in pore fluid pressure will eventually change the compactional shear to dilational shear, not because the stress regime is changing, but it will eventually change the pattern of the flow from cataclysmic flow, localized cataclysmic flow, to a granular flow, right? Excessive amount of pore pressure, that means excessive amount of fluid injection, will eventually lead to loss of cohesion, and fluidity will increase in the system, and that eventually turn into a granular flow. And for granular flow, the dilation is a major component of deformation, right? So pore fluid, and another thing is that if you have remembered the Moore Coulomb criterion, tau, that becomes the cohesion plus mu times sigma minus TF. This is the pore pressure. So if you reduce, I mean, if you increase the pore pressure, the shear stress will decrease, and the decrease in shear stress will eventually lead to the dilation. With increase in pore pressure, the effective normal stress will decrease, and that will lead to reduction in shear stress in the system, that will eventually turn to dilational shear. So that is the main explanation behind the effect of pore fluid pressure in shear localization. So pore fluid pressure plays an important role, especially in this case. But because if you go to ductile regime, in case of ductile regime, if you increase, so there is very small role of the porosity in case of a ductile material. So porosity itself is a presence of voids within the material, and that eventually decreases the cohesion. Now for ductile deformation, the cohesion exists pretty much throughout the stress strain curve. That is the that is the fundamental of ductile deformation. That is, and in that case, the pore fluid pressure doesn't play that much role. External fluid can obviously be present in the system through cracks that could be filled by fluid, and the presence of fluid will only uh, weaken the system pretty much. And this weakness, externally imposed weakness on the system, will eventually assist the system to be more compact and narrower, the localization, then it becomes wider. Right? So for a shear zone to become wide in the present in ductile shear domain, the fluid won't be a key component in that case controlling the deformation. But for brittle shear zones, the existence of external fluid will eventually lead to the dilation or widening of the shear zone through this kind of mechanism. Okay, so this was an easy one. So let us move on to the next question. So the question says that at the surface, a granite block is subjected to a normal stress of 100 MPa. The block is then transferred to a depth of 10 kilometers, and then new normal stress becomes 200 MPa. Given the normal geometry conditions, calculate the difference between the shear stress at the surface and at depth of 10 kilometers using Byerle's law. So you have to remember the Byerle's law in this case. So what is Byerle's law? Can you say? Or I mean, if you have gone through the lecture.
So there is two law. If
Yes.
for less than 100 less than 200 MPa, there tau c is equal to 0.85.
Exactly. So for
sigma n,
tau c is equal to 0.85 sigma n for pressures less than 200 MPa, and tau c is equal to 60
MPa
megapascal plus 0.6 sigma n for pressures greater than 200 MPa. So this is the critical shear stress, right? And normal stress relation. And Byerly's law essentially tells us that the coefficient 0.85 and 0.6 are coefficient of frictions, right? For crustal materials, undergoing deformation. So we have to apply these two laws to calculate what will be the difference in the shear stress between the surface and at the depth of 10 kilometers, right? So first of all, we see that at the surface, the stress, the normal stress is 100 MPa. So at the surface means we should apply the first law. That means tau c is equal to 0.85 sigma n, right? So at surface, tau c is equal to 0.85 times 100. That means 85 megapascal, right? Now it has been given that at 10 kilometer depth, sigma n is 200 MPa. Fine. And then we have been said that use normal geobaric conditions. So what is the normal geobaric gradient? That being 0.3 kilobar per kilometer, right? This is the normal geobaric gradient. We talked about this in the last class. So eventually, if we multiply with this gradient with 10 kilometers, we will get the depth, the pressure at 10 kilometer will be what? 0.3 times 10 means 3 kilobar. Now you remember the condition, 1 kilobar is equal to 0.1, sorry, 1 bar is equal to 0.1 megapascal. 1 bar is equal to 0.1 megapascal. So eventually 3 kilobar means 300 megapascal. So at 10 kilometer depths, we are exceeding the 200 megapascal criteria. So therefore, that means we have to use the second law to calculate the critical shear stress at a depth of 10 kilometers. Right? So at 10 kilometer depths, the sigma in is given as 200 megapascal. So therefore, tau c prime, it will be 60 plus 0.6 into 200. Right? So this will be 120 plus 60, which is 180, right? 180 megapascal. So the difference in shear stress which is del tau c is equal to tau prime c minus tau c, 180 minus 85 is 95 megapascal, right? So this is the answer. We will get a 95 megapascal of difference between the shear stress if we follow the Byerly's law of friction. Okay, so this was question number 4. So let's move on to the next question, which is question number 5. And it says that at a given microstructural configuration, the average dislocation nucleation length of a bulk polycrystalline metal is 14 nanometers. For the given material, if the average Burger's vector is 4.9 angstrom and the material is deformed at a strain rate of 5 into 10 to the power minus 6 per second, calculate the mean dislocation velocity assuming a pure exponential flow law. So there are few things to remember. First of all, assuming a pure exponential flow law means, if you have remembered, dislocation, sorry, dislocation mechanism can occur in two ways: dislocation glide, which is limited by obstacles in most cases, and the other one is dislocation creep. Right? Dislocation creep involves dislocation glide as well as climb. Now, what are their mathematical expressions? For dislocation glide, we get strain rate as a function of e to the power stress, right, in exponential form. But for dislocation creep, we get a times sigma to the power n, which is, so this one is exponential power, exponential flow law, and the other one is power law flow law. Right? So whenever there is a power law flow law, that means there is dislocation creep, which where n is the stress exponent of the system. But whenever you're talking about dislocation glide, there will be no climb, right? So in this case, in this problem, it has been given that you have to assume dislocation glide. That means there is no climb. The dislocations are purely slipping. It either and the simplest assumption is that it is a edge dislocation motion, right? No screw dislocation motion is involved, only edge dislocation. Okay, so we are talking about only edge dislocation, and for edge dislocation, if there is a glide happening, that means the dislocations are slipping along a particular slip system. That means to calculate the dislocation velocity, you should apply the Orowan's formula, right? So based on these assumptions that dislocation with pure exponential form means dislocation glide, and that means assumption is that it's edge dislocation, and from that, if we want to estimate the dislocation velocity, we have to apply the Orowan's equation. So what is Orowan's equation? So it has been written as strain rate is equal to rho B.
Rho BV.
Yes. So this is the dislocation density. B is the Burgers vector. And VD, the dislocation velocity. Right? Now, what we have been given? We have been given with the strain rate. We got the strain rate. And we got the Burgers vector. So if we could determine the dislocation density, we can easily estimate the dislocation velocity, average dislocation velocity, or the mean dislocation velocity. So dislocation density is basically the inverse of the square of the mean nucleation length. That's it. It was even in the Orowan's formula. So the length is been given, that is 14 nanometer, right? So 14 into 10 to the power minus 18, right? If you take the square, this much amount is your dislocation density per meter square. So the unit is meter inverse, right? So if we calculate this, it's a big number to calculate in calculator. 1 divided by 14 into 10 to the power minus 18. So it's around 7.14 into 10 to the power 15, right? 7.14 into 10 to the power 15 per meter square. So this is the dislocation density. B is the Barzel vector given as 4.9 angstrom. That means 4.9 into 10 to the power minus 10 meter, right? This is the unit of angstrom. And using these values, we can calculate the VD, that being the strain rate divided by rho times V. That means 5 into 10 to the power minus 6 divided by 7.14 into 10 to the power minus 15 into 4.9 into 10 to the power minus 10. Sorry, it's not minus 15, it's to the power 15. I've written wrong. 10 to the power minus, it's just 15. So it's 5 into 10 to the power minus 6 into 10 to the power 5, right? Divided by 7.14 into 4.9. So what will be the value? So 0.5, 0.5 divided by 7.0.5 divided by 7.14 times 4.9. So it's 0.0143 meter per second. Right? So it's near about 1.4 centimeter per second. This is the dislocation velocity. So this is how we can use the Barger's vector, the Orowan's equation, to calculate the dislocation velocity. Okay, moving on to the next question. It says that the increase in yield stress of a material due to repeated deformation at a constant temperature can be related to option A, obstacle limited dislocation climb, option B, strain hardening due to obstacle limited dislocation glide, option C, decrease in dislocation density, and option D, increase in frictional heat due to repeated deformation.
Answer will be B, strain hardening due to obstacle limited.
Exactly. strain hardening due to obstacle limited dislocation, right? So what happens during repeated deformation? So that is called cyclic deformation experiments. So the general idea is that, so you have a stress strain curve. I have to draw a bigger one. So this is your stress and this is your strain. This is the curve. So generally a material, say for example, this is your yield strength. You deformed the material up to this strength, which is sigma 1, say for example, and then you unload it, right? The load is being unloaded. So what will be the path? This will be the path. So this is the elastic portion, and the material will exactly follow during its unloading or the removal of load. It will essentially follow this elastic path, and this much amount of plastic strain will be induced into the material. Now, if you again try to deform the material, it will start from the same path and eventually reach this load, and then so up to this portion, the elastic limit has been extended. Previously, the elastic limit was up to this, but now the elastic limit has been extended up to this, and then is sigma 2, and then you again unload the material. It will then again follow the same elastic path. This much amount of plastic strain will again be induced into the material, and then if you again load it, it will follow the same path and then again go like this, and then eventually at some point the material will break. But every time you are repeating this cycle, you are getting an extra amount of stress to reach the yield point. That means the yield is increasing. So this is how the yield strength increases during repeated loading test. During repeated deformation. Now, what is the cause behind this? So say for example, you have a polycrystalline sample. So this is your block of sample, then there are grains. Okay. So once you compress it, to accommodate the strain, the material will develop some dislocations within it. And then if you try to repeatedly load the material, what will happen? Each of these grain will accommodate more and more dislocation. And eventually, this is how you increase the dislocation density. So with repeated deformation, the strain is accommodated through an increase in dislocation density. Now, say for example, how dislocation density. So this thing becomes very much, counterintuitive to think about, right? what are actually dislocations? Dislocations are defects, right? So if you have a defective material, what should it generally do? Whether should it increase your strength, or it, it should decrease or weaken the material? What would happen if generally for a given defect?
It is a weaken the material.
Yeah, the thing is that in common notion we should think from common logic is that, okay, so if you are introducing much amount of defect, so the material will become weakened, but not the case, because eventually dislocations move to accommodate the strain. They glide, they have a certain velocity for movement, right? So the strain is being accommodated by dissipation of energy through dislocations. Now suppose you have a lane and there are few traffics through that lane, so the cars will move slowly, but eventually if you stop every car in every signal, traffic signal, eventually the road will become crowded and there will be very much long jam in the road, and then all the cars will try to move randomly away, passing each other, taking over, and they are all trying to pass the signal to go their destination. So eventually what will happen, the cars will collide and the road can't be clear anytime, because the more the cars will try to pass each other, they will become more jam packed and eventually collide with each other. Same goes with the dislocations, because if you increase the density of dislocations in a particular material, the dislocations do not get enough space to move away from the point of nucleation to the other place so that it can dissipate the energy and release the strain. So that can't be an option if you increase the dislocation density up to a certain, critical value. After that case, what happens? Dislocation entangle with each other. That is called dislocation interaction. Dislocations have signs, just like electrons and protons. They are positive and negative. Dislocations do occur in different polarities. They have different directions of movement. If you put together two opposite signs of dislocations, they will generally annihilate and eventually end up releasing the energy. But in a system, if you keep on increasing the deformation, since the orientation of the crystal is not changing, it is very much difficult to produce different orientations of dislocation. So the dislocations that are being generated, they are also of same sign, right? So in a highway toll, you will see there are different lanes for trucks and small cars and bikes and cycles, and there are different lanes, right? So that means they are classifying different categories of vehicles from there. Now, in a small lane, if you push same kind of vehicles all together, what will happen? It will become crowded, right? And that same goes on with the dislocation. So that the increase in dislocation density eventually means that the probability of having same sign of dislocations will also increase. And this increase in dislocation density will eventually impede the motion of the dislocations. And if the dislocations can't move away, they will repel each other. And this repulsion will eventually uh, make the material harder even to accommodate the strain. So that is called strain hardening. So the concept of strain hardening is that if you keep on the temperature constant and repeated deformation takes place within the material will become strain hardened such that it will lose its ductility, and eventually the material will go on to rupture, right? So strain hardening decreases the ductility of the material for a given temperature. And repeated hardening eventually leads to rupture of the material. So that is how the increase in dislocation density plays a role in strain hardening. Okay, so we move on to the next question, which is question number 7, which says that which of the following phenomena causes a crystal to store energy and become metastable? Thermal agitation, long-range elastic interactions between dislocations, and interstitial vacancy fill-up. And option D is athermal dislocation climb. So think about, just now we discussed about the concept.
How a thermal dislocation climb will happen? It will happen only when sigma effective will increase when there will be agitation in.
Exactly. So athermal dislocation climb is a wrong concept. Exactly. So this is a wrong option. Now, what will thermal agitation do to a crystal? So thermal agitation means we are increasing the kinetic energy of the system.
Yeah.
So if we increase the kinetic energy of the system, what will happen? The heat will eventually dissipate. Can the material store the energy? Can a material store the thermal energy? Is it even possible? Say for example, you have a quartz, right? And how can you increase the thermal agitation? You have only to, it is only possible if you increase the temperature, right? Otherwise, it is not possible for you to provide thermal agitation without any kind of temperature. So if you keep on increasing the temperature, what will happen? You are providing thermal agitation to the system. So it will eventually lead to the phase transformation. From solid, it will turn to liquid, right? So that's how the material will use or utilize the energy you are providing, and it will eventually transform to a new phase, a new thermodynamic phase. It will be liquid, and eventually, if you keep on temperature, increasing the temperature very much high, say for example, you provide 1 million degrees of centigrade temperature, so it will vaporize, I guess, going to the vapor state or the plasma state. It can happen, right? So thermal agitation does not help the material to store its energy. It will eventually lead to formation of a new phase. So that's how we can eliminate this option as well. Now, for interstitial vacancy fill up, to provide if there is an existence of vacancy, that means the material itself was in metastable position, because vacancy will lead to instability. We discussed in the first question, right? Now, if you fill up the vacancy, what will happen? It will again come to the equilibrium position of energy in terms of energy. So if there was vacancy, and without any kind of filling up of using external atom or any kind of doping, the material would have remained in a metastable position or metastable thermodynamic condition. But filling up the vacancy will eventually lead that to going on to the equilibrium condition. So this is also not an option in this case, right? So what is remaining is the long range elastic interaction between dislocations, and that's what we discussed in the previous question, right? In question 6 we talked about strain hardening, right? So what is happening here? Because in strain hardening you're increasing the dislocation density, and eventually if you keep on increasing the dislocation density of the material, the dislocations with same sign or same polarity, they will repel each other. They are trapped within a crystal, they can't move away, they are constantly repelling each other, and you again are providing some external stress. So that's how the material will store its energy, because it has a very high amount of repulsion within it through dislocation interaction. Now, once you remove the stress, material will automatically try to recover the stage and it will show dynamic recrystallization. So this is how the process goes on. You keep on increasing the dislocation density. Eventually it will lead to the interaction of dislocation such a way it produces a long range elastic interaction. Long range elastic interactions mean the repulsion between the dislocations can send them apart a characteristic length scale that is much larger than the grain size itself. That is the long scale elastic interaction, long range elastic interaction. It's taking in a longer range. You're storing some. Say for example, if you've taken a bag full of magnets and somehow you blocked all the opposite poles with some non-magnetic material coating, etc. You put some sponges and so on, so that the attraction between opposite poles become very much feeble. And now you put thousands of these magnets in a ball, so in a sack of in a plastic bag. What will happen? They will try to repel each other, right?
Repel each other.
So yes. So once you release them from the bag, what will happen? They will move away in a very high velocity from each other, right? That's what happens when you try to forcibly put the same poles of magnets with each other. They store this energy, and once you release the magnet, they go away from each other. So that is the long range interaction. This is an elastic interaction, and the same thing goes on with this dislocations as well. So repeated deformation and increase in and increase in dislocation density eventually leads to long range elastic interaction between dislocations and that produces strain hardening in a material. Okay, so this was our 7th question. So we have 4 more questions left. It seems that we can finish our class pretty soon before 6. Okay, question 8. A material is undergoing dynamic recrystallization in a high pressure, high temperature regime, showing bulging, subgrain rotation, grain boundary migration. For each of these processes, choose the correct order of evolving dislocation densities for a given single grain. For option A is rho GBM is greater than rho BLG, which is greater than rho SGR. Option B, rho BLG is greater than rho SGR, which is greater than rho GBM. Option C, rho SGR is greater than rho GBM and which is greater than rho BLG. Option D is rho SGR is equal to rho GBM, but altogether greater than rho BLG. Think about the process. So what is bulging? What is subgrain rotation? What is grain boundary migration? What causes the grain boundaries to migrate? And once the grain boundaries migrate, what happens? Once the subgrains rotate, what happens? Once bulging is complete, what happens? So you have to think from that perspective. Why bulging is happening? Why subgrain rotation is taking place? Why grain boundary is migrating?
When weak stress strain curve, initially
Yes,
bulging starts. After
exactly.
yield, bulging starts. And again, after that, grain rotation happens, and in a straight line, then grain boundary migration happens.
So this is your undeformed rock. Your undeformed rock. You keep on trying the material to deform. So this is your yield stress. Say for example, this is your yield stress. So between this point, material is accommodating some plastic deformation. So in this state of stress and state of strain, the material is actually accommodating dislocations. So dislocations are starting to build up. So that means whenever we are talking about increase in the stress, we are marking that the dislocation density is eventually increasing. It goes to this highest point, which is the peak strength, and that's when bulging starts, right? And eventually from bulging it goes to subgrain rotation, and eventually when the steady state recovery takes place, we call that GBM. So bulging is a mechanism where the peak strength of the material is observed, and that point of time of dynamic recrystallization, it is at the highest dislocation density. So dislocation density has been built up so much. Now the material will start to release the dislocations. So first of all, to do that, they will align themselves first to accommodate the strain, to be closer to the equilibrium, and then they will repeatedly release the dislocations. So if you have a grain, so say for example, this is a grain, and this is another grain, and you're talking about this subgrain where you see that there is a high dislocation density, and there is a region just adjacent to that, there is a low dislocation density. So what will happen? The dislocations will move away like this, and eventually this will be created as a new grain boundary. So it will transform like this, right? So this is GBM, grain boundary migration. So that means the dislocations are released and the density is now equal, and so that there is the no signature of the metastability. So the entire purpose of these mechanisms is to release the energy in step by step sequential manner. So from bulging you go to subgrain rotation and you go to GBM. Eventually you're increasing the temperature as well. That means you are providing some energy to the system to release the dislocations and be free.
If sir, in bulging state, if
Yes.
subgrain rotation will not happen, that then the material will go to the strain hardening side.
Yes. Yes.
If
Eventually this is a form of strain hardening itself. Okay. So the stress strain curve can be like this as well. So this is your yield stress. This is your yield stress. A material can show curves in three different manners. This is ideally plastic behavior. This is ideally strain hardening behavior. For strain hardening, you can also expect this kind of stress strain curve. Although your yield point is here, you can eventually go to a steady state value, even having a strain hardening case. And you can follow the ideal plastic behavior, and you can also go to strain softening mode. The steady state, whether the steady state value is higher than the yield stress or lower than the yield stress, that defines strain hardening or strain softening. But the steady state value means you are entering the recovery stage of your dynamic recrystallization. It can also be during the
it will
strain
show,
softening.
it will show the release of stress.
Yes,
energy
release
releases.
of stress. So that means that once you enter the von Mises criterion, so this is known as the von Mises criterion, right? In the rheology classes, you have learned about the von Mises criterion. Von Mises criterion of plasticity. That means you are entering to the steady state flow of a material, right? So in that case, when when we see, so this is the stress strain signal. So this is the apparently we're getting these kind of data. Now the reason behind this steady state flow is that the material is going into the recovery stage. So it is releasing the dislocation. So now it is going on to the GBM mode, and it is releasing the energy that is being stored into the system, and now it is coming to the equilibrium condition. So that is the case. So you are actually first building up the dislocations and now releasing it, and that is why it is called dynamic recrystallization, because there is a constant dynamic, kinetics involved. Dynamics involved in terms of the gradient of dislocations and the stress. Right? So that being said, you can now easily say that in which case the dislocation density will be highest. So I guess option B is correct, right?
B.
So you go from bulging, then to subgrain, and then to GBM. That means you are eventually decreasing the dislocation density. So the correct option is rho BLG will be greater than rho SGR, and which eventually be greater than rho GBM. Keep in mind, I'm talking about completing the process. Showing bulging recrystallization means the bulging is complete. Subgrain is subgrain rotation, it is complete. GBM, it is complete. And eventually it will release the dislocation, so it will attain the recovery phase of dynamic recrystallization. Okay, so moving on to the next question. Which of the following curves represent the correct relation between the strain rate and grain size for diffusion creep? Four curves have been given. Which of them is the correct answer? So there are two kinds of diffusion creeps. One is Navarro herring creep. So what happens during Navarro herring creep? Materials diffuse
Go from inside the
inside to outside, right? So this is
inside.
how the diffusion pattern goes on. And what is the flow law equation? This is strain rate is equal to pre-exponential constant into exponent to the power minus q in h by RT times the differential stress divided by d square, right? So this is the grain size. And for cobble creep, what happens is that the materials diffuse from periphery of the grains.
Boundaries from boundaries.
Yes, it follows the grain boundary path. This is the diffusion path. And the equation is written pretty much in the same fashion, e to the power minus the energy for cobble creep times differential stress divided by dq. Right? So in this case, the strain rate is a function of inverse of the d square. So this is inverse square law. And this is inverse cube law. That means strain rate is proportional to the inverse of the Q of the grain size. So that means if we increase the grain size, the strain rate will decrease non-linearly as a function of grain size, right? The strain rate decreases non-linearly as a function of grain size. So in which of these graphs we see that strain rate is decreasing non-linearly as a function of grain size?
In B.
Yes, exactly. So option B is correct answer. So we see that strain rate is decreasing non-linearly as a function of grain size. Okay, so moving on to the next question, question number 10. For a given homologous temperature in the diffusion creep regime, which of the following mechanisms is likely to govern the superplastic deformation of a polycrystalline material? Option A, dislocation glide. Option B, dislocation creep. Option C, diffusion creep. Option D, dissolution precipitation creep. So I just want to share this thing as known as the superplastic deformation. So this is a new thing. So option C, its correct answers are both C and D, because diffusion creep, it of course will assist, and dissolution precipitation creep, this mechanism also facilitated or governed by diffusion of certain fluids of different concentration gradients. So that's how diffusion works, and dissolution precipitation creep is also facilitated in terms of diffusion. So what happens is that if you in a very high temperature, uh, high temperature deformation regime, say for example these are your grains, right? And now the internal elements are diffusing. Okay, so eventually you see that in this grain boundary, these grain boundaries, so if you are present there in fluid form and you're constantly adding up with diffusion, and there is external stress, keep in mind there is external deviatoric stress. So instead of, so grain boundaries become the weakest portion of all these grains, because so grain boundaries become the weakest portion in the um, in the polycrystalline assemblage. So what will happen now? So if you are applying the stress and now you're seeing that there is the weakest portion, so it will accommodate all the deformation. The deformation will be accommodated here. So eventually the shear stress component acting along these grain boundaries will try to move or the shift the grain boundaries. So if this was the initial arrangement, we will see that at final stage, the grains as a whole, they will shift. Right. And this mechanism is called grain boundary sliding. And entire crystals, they are just diffusing elements and nothing else is going on. There is no dislocations within the material, very few, because we are eventually in the diffusion creep regime where thermal agitation is high enough to contribute to the mobility of ions through the crystals, and eventually the grain boundaries become mobile. So they slide past each other to accommodate the strain. So this kind of deformation is known as where grain boundary sliding facilitates high amount of strain accommodation. That kind of deformation is known as superplastic deformation. When grain boundary sliding, GBS, so it is GBS. So when grain boundary sliding accommodates high amount of strain, it is known as superplastic deformation. Okay. And this kind of sliding where the grains are sliding past each other in this manner, this is also known as Ratzinger sliding. So this is a new thing I guess you have learned today. Just check it out in internet. You can know more about this Ratzinger sliding, grain boundary sliding mechanisms, and how narrow heading and cobble creeps are related to these mechanisms, and how superplastic deformation is also observed in earth materials such as quartz and olivine. Okay, so this is an exciting invention, discovery, that superplastic deformation do indeed occur in geological materials. That's why we see a huge strain amount in crustal shear zones or even mantle convections. Right? Okay, so moving on to our last question, which is two garnet grains are observed in thin section. The electron microprobe analysis, that means EPMA, of these two grains reveal the given two magnesium counts, sorry, manganese counts and manganese count maps. So choose the correct diffusion creep mechanism for two garnets. So you see the scale bar is given here, high concentration, low concentration of manganese in these two garnets, and these are the given option. So you can say that which one is the correct option.
I think, sir, C is the correct option.
Of A is DPC, dissolution precipitation creep, and B is cobble creep.
Yeah.
You're talking right. Okay. I think option B will be correct. A is showing Navarro heading creep and B is showing cobble creep.
Common.
So if you just remember what is Navarro heading creep, we see ions are moving in this manner from inside to outside, from inside flux to outside flux. So if there was high concentration of manganese, we will see a gradient like this, or eventually the reverse can also occur. Material is coming out from outside to inside. So outside there is low and inside there is high gradient. So anything which is involving the inside flux inside the crystal lattice, that's never varying creep, right? So materials either going inside or it is coming from outside, but inside the crystal.
Okay.
Right? So this will be never varying creep. But for case B, you can see that all the concentrations are related to the grain boundary. So
All
it
are
is easy, all are along the grain boundary. So the materials are diffused along the grain boundaries. So what kind of diffusion creep we see grain boundary wise, I mean boundary wise mobility of trace elements? So that's Powell creep, right? So option B will be the correct answer, because for A we see never varying creep and we see Cobble creep in this manner. So the fluid flux will generally continue this way from the outside of the grain. That means following the grain boundary. And this will eventually lead to the formation of this dispersed rim occurrence of diffusion within these garnets. So this was our overall discussion about today's topic, which was deformation mechanisms of material. So in the next lecture, I mean in week 7, we have lineations and foliations, right? So we will first understand. So lineations and foliations are also related to the calculations of structural attitudes. So the questions that will be there, they will both involve the interpretation of different kinds of lineations and foliation. It will also involve how the different deformations are superposed upon each other due to the interference between lineations, and some quantitative problems related to the bearing, I mean the trained plunge pitch of lineations and their attitude of foliations in stereo net projections. So all these things combined, we will have the discussions on the next Saturday. So for that now,
Sir,
till then,
sir, sir,
yes,
just,
yes, yes,
sir, just a
yes,
minute.
yes,
Sir,
yes, yes, sure.
before leaving, I want to know something related to this for DPC,
Yes.
dispersion precipitation creep. If
Hmm.
in a system, a magnetite
Hmm.
is converting to hematite,
Hmm.
magnetite is
Hmm.
converted to hematite, and
Hmm.
uranium is associating with the hematite. Along with hematite, uranium is association is there.
Hmm.
So,
Hmm. Hmm.
is there possibility to calculate the mass transfer of these parts? This is possible to.
Actually, you can do, considering uranium as your trace element, but you need a source for that uranium.
Hey, source is there. Source is there. In the system, there is a uranium. There is a
Yes.
magnetite. Magnetite is converting to hematite. Oxidation is given, and this due to
Yes.
this oxidation, the uranium is reduced and associated with hematite. So, due to
Yes.
this mass transfer, we can calculate the mass transfer. Is there any mechanism by which we can calculate? Just now,
So
it's not that it gives answer in this time. If you
no, but actually, it is possible. People do this kind of calculations. So you have to do the trace element mapping techniques. Are just you need the EPMA data of that
okay,
hematite.
okay.
So EPMA data of the I mean in the entire thin section. Say for example the this mm, this uranium, they must be associated with some form of quartz, SiO2. So in the system there must be some presence of SiO2, magnetite, hematite. So you do an EPMA scan of the regions you are trying to. I mean, see for example, if there are high concentrations of hematite you observe in some place, so there must be some region where the region, I mean the area where it is hematite depleted. So the depletion, so the amount of uh, transfer, mass transfer that you're talking about, that will be calculated based on the Fe number and Ng number.
Okay.
So if you get the EPMS scan of these areas, so you can get the Fe and Mg numbers. And using the Fe and Mg numbers, there are some empirical formulas you can find in internet,
Okay.
in any kind of standard geochemical textbook, geochemistry textbook. So you utilize that Fe number and Mg number, and you utilize that Fe and you correlate that Fe and Mg number with the distribution of your uranium.
Okay.
And that's how you can find out the gradient or the slope of that linear correlation, and that correlation will eventually be useful for calculating the mass transfer. So this is a process. I mean, briefly I can say that this is how it is done.
Okay. Thank you.
Okay, thank you very much. So for today, I'm closing the discussion session, and we will meet on again on next Saturday. Thank you.
Okay. Thank you, sir.
Yeah, bye.